Everyone's ready. And we're very glad to have Walter Tholen today from York University in Canada. We'll be talking about spaces versus categories, perfect maps versus discrete co-fibrations. So you can start when you're ready, Walter.
Yeah, thank you very much. Thank you for having me. You see the title on the screen. It's based on joint work with Leila Yeganeh, who was a postdoc at York for some time. She's back in Iran right now. Maybe she's actually joining this, I don't know. So let me start with two classes of maps that, why this is not coming down here? There we go. Oh yeah, so first let me get an overview. So I want to start with two classes of maps that I use sort of as a platform to get into Burroni's T categories that he introduced in 1971, though it's quite an old subject. And I want to present them maybe in some new clothes and make a little bit of propaganda for them, because I think they're a really nice environment that sort of combines themes of monad theory, internal category theory, or briefly we could say it's an environment where you can treat side by side algebras, spaces, and categories. Then I go back to these two classes of maps and show that you can establish what we call a comprehensive factorization system in that environment. And at the end, I briefly will talk about current and future work. Somehow my computer doesn't want to move this easily. Okay. So what are the nice maps, perfect maps? So a map is of topological spaces. It's perfect if it is simultaneously proper and separated, proper in the sense of Bourbaki. This means it's a stably closed map. Every pullback of it is closed, and it's separated in the sense of fibered topology, meaning that if you take two distinct points in a fiber of that map, then they can be separated globally in the domain of the map. General topologists normally don't talk about proper maps in the sense of a pullback stably closed map, but they characterize them as being closed maps that have compact fibers, and that is, of course, equivalent. And now we go to a different environment, that of small categories. Everybody knows what a discrete co-fibration is. So the functor goes from E to B, and whenever you take an object in the category of maps or morphisms in B with whose domain comes from upstairs with an X in E, then you find a unique morphism from X that is being thrown onto the given morphism. And these maps are nice because they have good properties. Only the very first are listed here. But as I said, I want to use them to motivate Burroni's environment. So let me start with the discrete co-fibrations. So as I said, P is a discrete co-fibration. If you have a map U downstairs with a domain coming from upstairs, then there is a unique way of lifting this whole thing. Now you can express this, of course, in terms of a pullback property in sets. So if you have a morphism down here with a given domain that comes from upstairs, then there is a unique morphism F up here, whose domain is X, and it's being thrown to the morphism U. And surprisingly, and I realized that only quite late in the game, that perfect maps have exactly the same pattern. So the thing, of course, is that you must not think in terms of topology, in terms of open or closed sets. You have to think in terms of conversions. And if you characterize perfect maps in terms of ultrafilter convergence, then the characterization is as follows. You have a point in the base space and an ultrafilter that converges to that point. And that ultrafilter is itself the image of an ultrafilter from upstairs. Then there is a unique point of convergence up in the category E for that ultrafilter X that lies in the fiber of B. You can express it again as a pullback property in sets. So we have an ultrafilter X up here being thrown down to an ultrafilter here. And what is conv B? Conv B is all the pairs. First component is an ultrafilter. Second component is a point of convergence. And the first projection of this relation I sort of called suggestively domain again. So if you have this scenario, then there is a unique pair up here, but the first component is already determined to be X. So there's a unique point of convergence, exactly the same thing as before. So the only sort of difference here is here you have a morphism. And what is this thing? There, I mean, the codomain, if that is an arrow, is one thing, and the domain is a different animal. So, of course, we have all seen those things. For instance, think about Lambek's multi-categories, where the domains are really lists, finite lists of objects, and the codomain is a single object. So a multi-category has objects, has a set of morphisms. It has domain and codomain functions, where the domain goes from the morphisms to lists of objects. And then you have composition, which is quite clear. If you have one morphism and each of these morphisms is a each of these objects is a codomain of another morphism, then you have a string of lists up here, which you can combine by the monad multiplication of the list monad, and you get a single morphism. All right, so now we just replace sets by any category with pullbacks, and we take any monad on that category. There's no requirement of well behavior of the monad with the pullbacks at this point. And in order to define T categories, let's first define T graphs. So a graph comes with an object of vertices or objects, and an object of edges or morphisms, and you have a domain morphism and a codomain morphism, and that's all. And of course, the morphisms of such T graphs have two components, an object part and a morphism part, and things have to commute. You can sort of make the definition tighter by requiring that this pair D, C is monic. What you then get is a full subcategory of what I call relational T-graphs. Burroni called them regular. And you could specify this even further by saying, okay, we want A1 to be precisely TA0 and the domain morphism to be an identity morphism. Well, then really you have A0 and T of A0 and a morphism from TA0 to A0. So you get to the most general notion of algebra, as, for instance, one uses that in computer science, algebras or co-algebras in the most general sense. So now let's put a little bit more structure there. So now pointed T-graphs are graphs that come with an insertion morphism of identities, which is a morphism from A0 to A1. What you see up here, you can consider as the sort of discrete pointed T-graph, and you need these commutativity conditions. And of course, the morphisms now should respect this new component. If you play the same game as before and restrict yourself to relational pointed T-graphs, then I call them reflexive. And if you go one step further and even insist that the domain morphism is an identity, well, then you force this insertion of identities to be the unit of the monad, and I will then have just what we would call unary T-algebras. So in order to now have the composition morphism, you have to get a little bit higher up. You have to have an object of composable pairs, let's say. And to talk about associativity, you have to go one level further and even talk about composable triples. All this is just defined by pullback to make sure that the pairs compose correctly. And you have to play the same game at the level of morphisms. So then with this at hand, you can say what the T category is. So a T category is a pointed T graph that in addition has a multiplication morphism or composition morphism going from the object of composable pairs to the object of morphisms. It has to provide the correct domain to the composite. So the only hiccup here is that you have to really bring in the monad multiplication, just as you would do that for a Kleisli composition to make things work. And of course, when it comes to morphisms, then morphisms should respect the composition. And you know, to express associativity and neutrality laws, you have to play the same game like you would do in internal category theory, but nothing spectacular is happening here. Please interrupt me if there is any question or if I go too fast or whatever. Before I go further, let me just make this nice little remark that functors are special categories. In the sense that if you have a monad on C, then you can lift that monad to to the squares, you get a monad T squared, where the underlying functor takes a morphism from F to G to a morphism from TF to TG. That is the result of T squared. And the monad multiplication and the unit are just arising from the naturality squares of these transformations. Now, if you want to know now what is a T squared category, well, a T squared category would be consisting of two objects in the squared category with a domain and a codomain morphism, each of which have two components. And the same is true for the structural components here. And if you read all the equations and conditions component-wise, then they will tell you, oh, A arising from the domain and B arising from the codomain have to be T categories, plus F has to be a T functor. So there wasn't really a need to introduce anything new. Once you say what a T category is, you have already said what a T functor is. In addition, we can play the same game that we played before, in the sense that we can talk about those T categories for which the pair domain codomain is monic. These will be internal orders, T orders. And you can also take the case of the domain being an identity, and you get the usual Eilenberg-Moore algebras. So what we have established then is a network of categories. If we look at the bottom, everything is over C. We first introduced these naked graphs, then we made them pointed, then we had T categories. Then if you go to the column here, these are the things, the full subcategories that you obtain by looking at monic pairs for domain and codomain. And here is the algebra side. There are lots of connections between these categories. You can ask a student to work out all the existence of left adjoints and other things. There's lots of room for playing with these things. So special cases, of course, are internal structures, internal categories, internal orders. Nothing new when you do the Eilenberg-Moore category, but beware if you take the sort of naked, unstructured algebras. These will be objects with an endomorphism, so that's not the same as C. You get the multi-categories, in this case for the Lisp monad, multi-orders, monoids. But from the topological side, we want to look at the ultrafilter monad as induced by the adjunction between Boolean algebras and sets, where on each side you have the HOM given by either the two-element set or the two-element Boolean algebra. And if you now consider internal orders in sets, these will be precisely topologies on the underlying set of objects in terms of ultrafilter convergence. And before explaining the reflexivity and transitivity, let me just note the following. We all know that Manes was the first in his dissertation to observe that compact Hausdorff spaces are algebraic in the sense, every ultrafilter converges to one point and it satisfies this map satisfies the ultrafilter algebra axioms. Barr shortly later said, okay, if you don't take a map but just a relation, saying ultrafilter might or might not converge, and it might converge to Marius point, then subject to relational algebra axioms, we will get precisely topological spaces. But I think the history goes further. If you open Hausdorff's book, then you will, first of all, realize that a good third of that book, the first 6 or 7 chapters, I don't remember precisely, are about ordered sets. And there are crucial sort of remarks in that book where he muses that, okay, we could have an order not just between points, but between things that are more general than points. And my take of this was that the Hausdorff really imagined that topologies might be given and described by a convergence relation. Of course, that was the theme, but the way he talks about this makes it clear that a topology is a generalization of a preorder. And I would suspect that Cartan, but that's just a guess of mine, might have had the same take on this. So what are the 2 axioms? We have to have that if you have any relation between ultrafilters and points, fixed ultrafilters have to converge to that point. And if you have an ultrafilter Y converging to a point Z, and the ultrafilter itself is the point of convergence of a big ultrafilter on the set of all ultrafilters on X, then you can form the diagonal ultrafilter. The sigma stands for applying the composition rule of the ultrafilter monad. So this thing is called as a Kowalski sum of this big filter that has to converge to Z. The way you can sort of elementarily think about this is think just about convergence of sequences. So if you have a sequence Y converging to Z, and every point of the sequence is a point of convergence of another sequence that goes to that single point, then you can take a diagonal sequence, and that has to converge to Z. That's the axiom. Of course, I have talked here only about ultrafilter orders. You could also talk about U categories. And here comes the first confession. I don't actually know what they are. Of course, I can write down what they are. I strongly suspect that they are the same thing that that we introduced in a paper with Clementino in 2003, where basically you come from the notion of multi-category, and instead of lists of objects as domains, you have ultrafilters on the set of objects. And you write down the category axioms. But I still haven't really managed to establish this equality. All right, so just a few remarks on what you can say about these connecting functors. Each of these categories that you see on the screen is fibered over C, except for the Allenberg-Moore category, of course. The arrows preserve Cartesian morphisms, and then you can do your exercises proving things like if the base category is complete, then also the fibered category will be complete. But I have to say this with a slight warning. It's not as easy as when you do it for the Eilenberg-Moore category. In particular, it is not automatically true if you have a type of limit of a specified shape downstairs, that the same thing automatically happens upstairs. So you need other things to combine things, but I will say a little bit more about it when we need it. We saw that in at least one example, we got, for the ultrafilter monad, we got topological spaces here that would be over sets. And of course, that's not just a fibration, that's a topological category. And you can establish this more generally when C is well powered. And in that case, of course, you can also lift co-completeness. Nothing of this is surprising. Most of it is in some form available already in Burroni's paper, not easy to read. So the terminology here is a little bit different. Also, the next thing, what I want to say is not unexpected, but then when it comes to the comprehensive factorization, I think then we get to more surprising territory. So the only routine thing that I wanted to add here is that you have, of course, that cut T or T and so on behave well if you change the parameter T. So if you have two monads on categories C and D respectively, both with pullbacks, and if the functor part of a monad morphism from T to S, where I let the functor part dominate the direction of the arrow, if that preserves the pullback, and the transformation, of course, is compatible with the monad structure, then you get a network of arrows from top to the bottom row. And these arrows are nice. They will preserve Cartesianness, etc. There's one important case when the category D is the same as C, and S is the identity monad, and F is the identity functor, and the transformation is a unit of the monad T. Then this shows that every T category has an underlying internal category in C. So for instance, what this means in the case of the ultrafilter monad, and you go to ORT, then you have a topological space, and a topological space has an underlying order given by the specialization order. All right, so now let us go to the comprehensive factorization of CAT. This is a well-known paper by Street and Walters from 1973. Of course, comprehension, that set comprehension is part of an adjunction is Lovier's idea. I don't know, it must be somewhere late 60s. I now don't remember the precise reference, but how does it go? So we have a functor from A to B, and we want to factor it universally through a discrete cofibration. So what we do is we take the left Kahn extension along F of the functor that has constant value singleton set 1. And then we take the element construction of this set-valued functor. that is actually given by forming the co-limit of an adjusted Hom functor. So he takes this element construction that is, of course, a discrete co-fibration. And then you have an induced functor that establishes the factorization. And that functor is whatever you want to call it, initial, limit invariant. In any case, it has the property that if you compute the limit in some category of this scheme, of a diagram of this scheme, then you can also pre-compose that diagram with L and still have the same limit. And that is all well known. Okay, so what about the same thing for perfect maps of Tikhonov spaces? That goes back to Wyburn in 1966. He showed that every continuous map of Tikhonov spaces factors universally through a perfect map. But there was decisive work already by Henriksen and Isbell that precedes this. And then there are sort of many categorical follow-up papers, even though Ringel and Cassidy, Hebert, Kelly don't look at this particular example at all. In my paper of 1999, I give a sort of general categorical way of dealing with this particular situation, but I think this is quite nice here. So you take your F and you apply the Stone-Czech compactification to this map, so you get a naturality diagram, and you really factor in the category of arrows. And how you do this is you take beta F, beta Y, take the pullback. Now, clearly, this map is perfect because any map between compact Hausdorff spaces is perfect. And though the only burden now is to show that the induced map that you have here is really the other part that you need for the factorization. And what is important to know here is a map is perfect if and only if the naturality diagram of that map is a pullback, and it is anti-perfect precisely when the image of that map under the Stone-Czech compactification is your homeomorphism. I think it's in this Henriksen-Isbell paper that you have this first characterization, really. All right, so now we want to do this in cat-T. So first of all, it is very easy to say what in cat-T a perfect or discrete cofibration should be. It should be that this diagram is the pullback diagram, because this is precisely how I started the talk when I characterized discrete cofibrations and perfect maps. Exactly the same picture. So the question then is, you have a good candidate for a factorization system on the right-hand side, the right part of a factorization system. So the first general question is, when you have such a class, how do you determine that there is a factorization partner, provided that the category has pullbacks? I don't think this is written down very clearly in the literature at all. So, I mean, there are sort of variations of what you see on the screen, but I don't see it really written in any earlier text or paper that I'm aware of. So clearly, necessary conditions are that M must be closed under composition, that it be stable under pullback. When I say stable under pullback, then I mean stable under every pullback, which means that M has to be also closed under precomposition with isomorphisms. That is hidden in this second bullet. The most important condition is that when you look at the category of objects over B and consider the M morphisms over B as a full subcategory of that category has to be reflective. This is, in my view, the most basic notion of unique factorization, and it goes back a long way, predates all the other sort of standard orthogonal factorization papers that we are aware of. And these conditions are necessary. So there's no other condition on M. So now we go to business. So we have our program set out. We have to prove these three conditions. Well, one is very easy. If you vertically paste pullback diagrams, you see immediately that the class P is closed under composition. No problem. So let's go to pullback stability. Well, that is easy if you assume that T is, if T, the endofunctor of the monad preserves pullbacks. So how would you do that in this case? You have two maps, F and G. Oops, oh, that was bad. That was bad. Sorry. Somehow I have difficulty moving this forward, but now it goes better. So what you do is when you are given F from A to C, B from G to C, you form simply the pullback of the object part, you form the pullback of the morphism part, and the T image of the object construction is still a pullback in this, under this assumption, and you have induced morphisms, and somehow you can lift this game with enough patience to also get the structure from ABC onto P, and you are done, because if G is a discrete cofibration or perfect, then the front is a pullback. Then also this passage here, if you paste, is a pullback. This means this is a pullback. And then you can cancel and you see, bingo, the back panel is a pullback. No sweat. But now, what do you do if T doesn't preserve pullbacks? Well, then you have to draw a bigger diagram. You start off the same way as before. You form this pullback P0. You still form this pullback of F1 and G1. The only thing you must not do is believe that you're already done with this. You also take the pullback of TF0, TG0. This, of course, is different from the T image, but there is a comparison morphism. So now you see that, as before, this lower square in the back here on the left is still a pullback by the same token as before. But you want really that when you now take the pullback here, then you get a pullback over there. So now you say, okay, this should be the thing that I need as an object of morphisms. Okay, that's fine, but now you have to go through the trouble of, in particular, establishing the composition law of this, which is sort of straightforward if you don't have this deviation, but it's not so straightforward if you have this defect in there. So basically, in some sense, you first have to have a kind of fake structure on this P1 tilde and then go further. I'm not very happy with the proof we have. It goes over 9 pages in the printed paper. So if somebody can do this more elegantly, I would be very happy to know. So in any case, we do have that even without pullback preservation of T, which is important because the ultrafilter monad doesn't preserve pullbacks. We do have this pullback stability, and if we are able to now also show the reflectivity part, which unfortunately is even nastier than the pullback thing, then we would finally have a theorem that would allow us to say we have a comprehensive factorization system in cat T. Now, to get to the reflectivity, this, however, doesn't come for free. We still do it without pullback preservation, but in order to do so, we need co-equalizers of reflexive pairs, and we need to assume that these be stable under pullback, and the co-equalizers, these reflexive co-equalizers, have to be preserved by T. To give you an idea about the construction, let me show you just one slide on this. So somehow we want to universally assign to a morphism F a perfect morphism with the same codomain. So the first part is easy, and it's sort of interesting, and that's why I also say the whole thing sort of combines monad theory with internal category theory, in the sense we all know that we have nice reflexive co-equalizers in monad theory. That same is true for Burroni's T categories. You have always for every object this nice reflexive co-equalizer. And now having the F, the only thing you do is you have to manipulate this part. So you place it by TA1, and you have a morphism here. You have to do the same thing here, where, well, you could think of B1 as TB0 cross over TB0 times B1, that cancels out. You have pi 2 here. So somehow you have to make an effort to see that there is a reflexive pair, just like here, even at that level. And then you form the co-equalizer and get the object. Now the next part is still fairly easy. You have no choice how to form the set of morphisms, because you want to have a discrete cofibration. So you have to define it as a pullback. But from then on, it is not so easy anymore, because it starts off, you get your domain morphism for free. But what is a codomain morphism? Well, this is a pullback. So the codomain morphism is a morphism out of the pullback. There's no chance at this level to get it like this, unless you're able to present that pullback as the result of or the codomain of a reflexive co-equalizer. So somehow the reflexive co-equalizer that you have here, you have to here it is again with abbreviation, and somehow as we define C prime C, you have to go one level up. You have to establish this reflexive pair, form the co-equalizer, and then go down. But it really becomes, you know, a big test in your patients when you now want to push it again one level up and establish the composition law. Again, it's pretty long in our paper, and if one can do this more quickly, that would be nice. In the case that T is the identity monad, you can see a proof in Johnston's elephant, but it's very compactly written. And of course, it doesn't have the complication of the monad being involved. There's a nice paper by Berger and Kaufmann who established comprehensive factorization systems in a different environment. It doesn't, as far as I can see, include the internal category environment, but it includes the ordinary multi-categories in over sets. I should mention that, of course, if you have T orders instead of T categories and you do the comprehensive factorization, that stays in T orders. If you would specialize even further and go to Eilenberg-Moore algebras, then the whole thing becomes a joke because it's the trivial factorization system, isomorphisms, all morphisms. Every morphism between Eilenberg-Moore categories is perfect, just like every map of compact Hausdorff spaces is perfect. All right. So here comes a big disappointment. That's still work in progress. So we do have the comprehensive factorization system for Tikhonov spaces. But the assumptions that I have are still too strict for the ultrafilter functor. It doesn't preserve reflexive co-equalizers. Yet, for Tikhonov spaces, at least we have this factorization system. Dirk Hoffmann gave me a nice example that clearly shows why the ultrafilter functor doesn't preserve reflexive co-equalizers. It goes as follows. You take pairs of natural numbers that are adjacent or equal. And you have the two projections into the natural numbers. Of course, if you form the co-equalizer of that, that is a one-point set. The set of ultrafilters on a one-point set is a one-point set. However, if you take the images on the ultrafilter functor of the two projections, then you realize their co-equalizer cannot be just one point because it will never identify a fixed ultrafilter with a free ultrafilter. Because if you had an ultrafilter, say R on the set capital R of the relation, where the one projection sends it to a fixed one and the other to a free one, well, the first one, if it is fixed, then you get at most 3 element set in that ultrafilter R, which makes the whole ultrafilter fixed. Well, then also the other projection would send it to a fixed one. So the equivalence relation generated here cannot be trivial. So that's a disappointment, but we are working on it. I do know how to say when a T category is Tychonoff. But I haven't finished a proof on the comprehensive factorization on this. It will need some conditions, but I would say I'm sort of halfway done, although nobody knows this, as we know, if there is a dark cloud, there can be lots of surprises yet. Other things that we are working on with Leila is exponentiability and closeness. I haven't talked at all about the two categorical context. T is a two category, but you know, there's lots of preceding work on this, starting with Burroni's old paper. But for instance, to have two cells, you have to assume that T is pullback preserving. It cuts off examples right away, and as the first two bullets show, I still busy trying to resolve this part. All right, I think that is it. I don't know how I'm doing with time. I think I have been doing quite well. So thank you for listening.
Okay, thanks very much for a nice talk. So we can have a silent round of applause, as usual. And then if anyone has any questions, you can go ahead and ask, or comments as well.
Walter, are your alter categories related to alter categories of Mackay?
Sorry, which types of categories?
Alter categories, your alter categories.
Sorry, I don't understand the term. Accessible, you mean, or?
You talked about alter categories in your joint work with Manuel.
I don't understand the type of categories you're talking about. I don't understand the word.
Ultra.
Ultra, oh, ultra. No, we came up with this, and it's quite a complicated animal, even in this 2003 paper, and I don't think that anybody has ever looked at it again. You see, in that paper, we really introduce these TV categories, and in this case, for ultra categories, the V is just set, but this whole environment then requires you to extend the monad to a Lux monad on rel. All this is fine when your V is just a quantile. This means a thin closed category, but as soon as it is fat or not thin, it becomes very complicated. So the notion is complicated, but I do think it is the natural step up, or is a natural amalgamation of the notion of space and category.
So it is not related to ultra categories of Mackay, no.
No, the ultra categories of Mackay, they use the ultra products, right?
Yes. No.
Yeah.
No, they use the family of ultra functors.
Yeah. I'm not 100% sure. I'm not 100% sure. I sort of doubt it, but I'm not an ultrafilter, expert. I would say I love the results, but sometimes I need. For instance, I worked with Jan Reiterman, who was wonderful with ultrafilters, and it helped me a lot. There are people in more set theoretic than me who can, create these ultrafilters like miracles, and I can't do this.
Because these Mackay ultra categories were used by Lurie in his.
So I really have to look at this.
Yes, because
I really have to look at it. Thank you very much.
It seems to be an important concept, yes.
Mm-hmm.
I just had a look at NCAT, and they say these three concepts are all different. Yours, Mackay's, and Lurie's.
I see.
Lurie's and Mackay's are related, at least.
Okay. Yeah, my feeling was that nobody has ever taken this up further, including the authors of the 2003 paper.
Can I just ask a question then? So the ultrafilter monad doesn't preserve reflexive coequalizers, right?
Right.
So I was just wondering, does it preserve coequalizers of equivalence relations? Because sometimes in monad theory on set, at least, there's all these results where you have things about coequalizer equivalence relations, but not reflexive coequalizers. There was like Ruskin's monadicity theorem and stuff like this.
Right.
I was just wondering if you could maybe do something using.
Simple answer. Every monad does. Every monad on set.
On set, yes.
Preserves coequalizers of equivalence relations.
But unfortunately, it will not help me, right?
No, I didn't try to help you. I tried to answer John's
Yeah.
question.
Oh, it's true, yeah, sorry. It's not very helpful.
Yeah, unfortunately, I don't have equivalence relations. I have just reflexive pairs. So even if T is, so if you have T the identity into the internal category case, so domain and codomain morphisms are reflexive, but that's all I can say really. And you need that. They're still far from being a kernel pair or anything.
There was one question in the chat, John.
Oh yeah, so there's a question in the chat. The person who asked it had to go, but they asked if could ask the question that they've written here, which is, the comprehensive factorization system in CAT is inspired at least in part by Levier's comprehension schema. Is there an analog of the comprehension schema in this setting that justifies the naming convention in this more general setting?
Well, I went, in naming this, I used Street Walters. I mean, they call this a comprehensive factorization system. Berger and Kaufman do the same. So that is the role model. There is some literature between Levier's original paper and the Street Walters paper, in particular by John Gray. And we point this out in the paper with Leila. I think John Gray made already a big step in sort of giving a categorification of Levier's original observation. So replacing basically set through by cat. And we explained that in the introduction to our paper. So I think if I am asked to give names, then it's you know, Lovier, Gray, Street Walters, and then everything else is past history. Yeah, so if I come back to this question, of course, you can say, well, if you look at the anti-perfect perfect factorization, what does it have to do with set-theoretic comprehension? Well, I don't know, nothing, right, probably.
Any more questions or comments? Well, if not, then let's thank Walter again.
Okay. Thank you very much.
Thank you. And next week we have Nathaniel Arcor, who is the person who asked the question in the comments. So he will be talking about higher order algebraic theories and relative monads, which is coming from, inspired by type theory, I think. So, so that's next week. And so we can stop recording.
It will be again at 1 o'clock, I suppose.
It will be back. It will be back at 1 o'clock.